Hello, and welcome to another Applied Flow Technology webinar. Today we are going to be discussing non-Newtonian fluid models and how they are used in AFT Fathom. My name is David Despars. I'm an applications engineer here at AFT. I work primarily on our support and training team, and this is one of the things that people will often write in about as they're trying to model non-Newtonian fluids. They have data and they're trying to figure out how to apply it within the software, so we're going to discuss that here today. So our agenda is going to be covering viscosity back at a basic standpoint. We're going to discuss the different non-Newtonian models that are within the software along with their equations, and then at the end have an application. So viscosity, let's do a refresher on viscosity. Viscosity is the fluid's resistance to flow. If we take a low viscosity fluid, this is going to flow relatively freely. Think water, acetone, gases. If we pour out a cup of water on a table, it's going to quickly disperse across the entire table and get your books, your laptop, your keyboard just soaked. If instead we're working with a high viscosity fluid, this is going to resist flowing to a greater degree. So think honey, mercury, pitch. If we instead were pouring honey or syrup onto our desk, it will take a much longer time for it to disperse. Instead, it will want to glop up and just stay in its general vicinity. So how do we quantify this in a numerical way? So if we were to instead picture a plate resting on top of a fluid, we can take this plate and move it at a constant force and velocity along the surface of the fluid. By taking this constant force over the area, thinking the plate that is in contact with the fluid, this creates a shear stress, so we can calculate that shear stress. The deformation that is happening to the fluid, or also the change in shape, location, how that's characterized, this is the shear rate, and it is of the fluid itself. So if you're thinking about that plate, the fluid particles that are along the contact with it have a kinematic boundary condition that must move with the plate, but the fluid particles that are below that layer are going to be less susceptible to moving, and they're going to angle with each other. So this gets us to an equation where we can say viscosity is equal to the shear stress over the shear rate, and this is for non-Newtonian or for Newtonian fluids, where there is a constant viscosity, a constant relationship between the shear stress, the constant force of moving that plate, versus the shear rate, at which rate does the fluid start to deform and move along with the plate. So we have different viscosity and non-Newtonian models within Fathom and Impulse. First, Newtonian. It would not be good software if we could not model Newtonian fluids. Other viscosity models include a paper stock model. We have a Duffy and Brecht-Heller. We can model the power law, the Bingham plastic model, the Herschel-Bulkley model, and this one at the bottom, homogeneous scale-up, which is based upon a correlation of other viscosity, shear rate, shear stress calculations. So we'll talk about that when we get there. Ultimately, what happens within Fathom when you change these different viscosity models? Your viscosity calculations are going to be much different. What does viscosity impact? That impacts your Reynolds number being equal to the density times velocity times diameter of your pipe over the viscosity of the fluid you're working with. Reynolds number will ultimately impact your friction factors. Friction factors will impact your pressure drop along the length of the pipe, and then the pressure drop calculations are going to impact your flow rate. So ultimately, how you choose your viscosity non-Newtonian model is going to impact your results. So it's ideal to be using the correct non-Newtonian model available. So digging a little bit more into these models, starting with the Newtonian model that we were discussing. The Newtonian model shear stress equation is your shear stress is equal to a viscosity times shear rate. Because your viscosity is constant, this is going to have a constant shear stress shear rate relationship. And if we were to map out instead the viscosity, that's going to be constant viscosity regardless of what shear rate you're working with. So pretty easy to figure out what the viscosity of your Newtonian fluid is. Some examples of Newtonian fluids include water, gasoline, alcohol, and honey. So even though honey is very viscous, or has a high viscosity, it is still a Newtonian fluid where it has a constant viscosity versus shear rate. The next model to discuss is the Bingham plastic model. This is going to be very similar to the Newtonian model, but instead there is a yield stress that must first be overcome for the fluid to be moving. And so it takes that into account, where your shear stress is equal to your yield stress plus the plastic viscosity times the shear rate. And so once that yield stress has been overcome to move the fluid, it will start moving at a constant relationship of shear stress shear rate, shown here. If we change that into what is going to be called the apparent viscosity, because it's not exactly the viscosity, but it's apparent. It's the apparent viscosity. We can then calculate that and show that on a graph. Some examples of Bingham plastic fluids include toothpaste, where you have to squeeze the toothpaste for it to start moving out of the tube, so it has to overcome that yield stress. Mayonnaise, chocolate, bread dough, a lot of food components can be modeled using a Bingham plastic model. Plastics and cement slurries. Our next model here is the power law model. Power law is going to start at the origin of shear stress shear rate. And your shear stress is going to equal a constant known as the consistency coefficient times your shear rate to the power of a flow index. And so due to that power, your shear stress versus shear rate equation or graph here is going to be moving off, is going to be bending along as shear rate is increasing. If n, our flow index, is less than 1, this is called shear thinning, also known as a pseudoplastic, and it's basically where the viscosity of the fluid is decreasing, the apparent viscosity of the fluid is decreasing as you are moving at a greater shear rate. So here's a graph of a viscosity versus shear rate in a linear scale, but instead if we were to graph it as a logarithmic scale, we can start seeing that linear pattern telling us that this is a power law fluid that we are working with. So if your viscosity model that you received, it comes in this form, then it is most likely a power law fluid. The nice thing about that flow index is it can also be positive to demonstrate shear thickening, also known as a dilatant fluid, in which the greater the shear rate, the greater the viscosity, the greater the shear stress, and it starts having a bend upwards. Some examples of power law fluids include polymer solutions, pseudoplastic, pigments, also a pseudoplastic, or starch solutions, this is a dilatant or clay solutions, where as you start mixing it at a faster rate, it starts resisting you more and more. The Herschel-Bulkley model is a combination in the Bingham plastic and the power law, and you can kind of see both of those features here, where we have a shear rate is equal to that yield stress that must be overcome, or shear stress that must be overcome, plus a constant times the shear rate to the power of n. And so you still have to overcome that yield stress in order to get the fluid to be moving, but even after it's started to move, the viscosity might not be constant. And so some examples of a Herschel-Bulkley fluid include paint, oblique, which is that kind of that fluid where it's like you can walk on it, but as soon as you stop moving, you'll start to sink. But as long as you are continuously adding pressure and force to it, it will kind of act like a solid, and you can walk across it. And another very popular Herschel-Bulkley fluid is blood. And so a lot of research needed to go into how does blood work within the human body so that doctors can help people. You'll notice here this viscosity versus shear rate. It looks linear when we're looking at a logarithmic scale, but it's not exactly linear, so it is slightly cantered. So keep that in mind, but it can still be just a way that you can indicate what fluid you're working with when you're looking at your data. We do have pulp models available, one being the Duffy model. This is going to be based upon correlation data from laboratory testing and pulp mill piping systems, so both labs and real world examples. It is meant to determine a minimum value of pipe friction loss that would occur using your pulp model, and it is intended that a safety factor is applied. It is intended that that happens. What safety factor should you use? This is up to your system designer's discretion. There are 21 pulp stock fluids to choose from within AFT Fathom, and it is important to keep in mind that these are only valid for 2 to 6% pulp consistency. So, because that's the boundary of the correlation data that was used for the Duffy model. A second model that we have for pulps is the Brecht-Heller method. This is also based upon laboratory testing and pulp mills piping systems. This is expected to be more conservative than the Duffy model and will predict a larger pressure drop for the exact same system. And we have 8 pulp stock fluids for you to choose from within the software. Rounding up the different models we have within the software is the homogeneous scale-up. This is going to be referenced from a group out of Georgia. 4 authors, Wilson, Addy, Selgren, and Cliff. They authored a book called Slurry Transport Using Centrifugal Pumps. Fun fact, this is the same book that we use for our SSL modules calculations, and a great resource if you're working in the mining or non-Newtonian or slurry transportation field. Highly recommend go get that book. It is very valuable. Within their book, they reference a Rabinowitz-Mooney technique. And ultimately what this technique is trying to, they were able to determine, these two scientists, they were able to prove that the wall shear stress and the value of 8 times the velocity of the slurry over a diameter of the pipe can be functionally linked. And ultimately what these two scientists were able to come up with is a scale-up correlation between different data sets. I like to think about these as like, if you think about the affinity laws for pumps, where you can just change the diameter or the flow rate of your pump, and how will that impact your pressure rise, etc. It's the same concept, but instead now we're doing for pressure drop gradients within pipes and slurries. This method can be applicable for both the laminar and the turbulent region. and this is meant for homogeneous non-settling mixtures. So the equations involved here basically say that the pressure gradient of the real world system that you are trying to build can be equivalent in the laminar region to the pressure gradient you would see within an experiment times a ratio of the pipe diameter experiment and the real world system. Same with your velocity in a common way, where you can say the velocity of your real world system will equal the velocity of your experiment plus that ratio. This has been expanded into the turbulent region, where you can see that the pressure gradient of the real world system is going to be the same as your laminar, but then the velocity profile will be slightly different, and that's also taking into account that turbulent regime and how does the wall stresses affect your fluid flow. So those are the calculations, those are the formulas that we have within the software in order to take your data from an experimental pipe flow of your working fluid and see how is that going to scale to your real world system. So we'll see this here in our example, but with the homogeneous you would have flow velocity and pressure gradient data available from your experiment. You would specify what type of pipe, what size pipe were you working with in order to get that data, and then you can then match it up to a new pipe that you're going to design for. And then it will correlate what is that pressure gradient going to look like, pressure gradient and velocity going to look like for that new pipe. So one of the big questions that we get from people is, you have data, what can you do with it? Ultimately, what AFT Fathom needs from you is your shear stress versus your shear rate data, or the coefficients of whatever non-Newtonian model you are choosing to work with. If this happens frequently, if the user has viscosity or apparent viscosity data only versus that shear rate, what you can do is multiply the apparent viscosity data by the shear rate at that data point in order to come up with a shear stress data point. And so this is a good way to be able to change your data from viscosity into shear stress, which ultimately Fathom needs the shear stress data. If you were working with this data in Excel, here's 4 different models. What you could find is your Newtonian model would create a linear curve fit for your shear stress, shear rate data points, and it will be a constant for your viscosity versus shear rate. If instead you were working with a Bingham plastic, that curve fit would still be linear, but it will instead have a y-intercept. If you were working with the power law model, you'll see a power law curve fit with both your shear stress versus shear rate data, as well as your viscosity, apparent viscosity and shear rate data. It will follow that same power law. And then with the Herschel-Bulkley, it will also kind of follow that power law curve fit, but it will have a y-intercept. And so what you might need to do is, if you have data and you believe that it is a Herschel-Bulkley fluid that you're working with, you might need to go find what that y-intercept is, which is your yield stress in order to get the fluid to be moving. You're going to need to calculate whatever that is, and then you can subtract that from your data set, get that curve fit, get the constants. But if you have shear stress versus shear rate data, Fathom can take that and give you the coefficients required. So as promised, we're going to do an example and look at a few of these non-Newtonian models and how can you enter the data. So this non-Newtonian, this example is off of our help site. This is also based upon out of that slurry transportation handbook. And in this example, we're going to be working with a phosphate slime clay water slurry, which we're going to treat as which is a non-Newtonian fluid that we are going to be working with. We're going to say we have example data of what is the velocity versus the head gradient for a steel 203 millimeter, also known as an 8-inch pipe. And we need to take that data and place it within Fathom. So in this example, we're going to start with just building our pipe model. It's going to be a super simple model of just a pressure junction leading into a pump that's in sizing mode, leading to another pressure junction 700 meters away. The example also goes on to compare 3 different flow rates that it's working with. The first one being a pump that's in sizing that is at a 720 cubic meter per hour flow rate. And for a nominal efficiency, we're going to say it's 75% for our example. Inlet elevation of 0 meters. And underneath the optional tab, we're going to give it some power data where we're going to say that it requires 75 kilowatts of power, and it'll have a motor efficiency of 95% at that 75 kilowatts of power. So I can quickly copy all that data from J2 into J5 using this copy data from junction tab. Press that, select all the points that I care to copy over, and now I'm going to change this to be the next level up of 1080 cubic meters per hour. We're trying to size this pump within a different range of flow rates, so the next tier would be 1080 cubic meter per hour for this example. And then for J8, we'll copy that over from pump 5, and this is going to be 1440 cubic meters per hour. All of my pressure junctions are going to be at 0 meters elevation, and we're going to start them at atmospheric 0 bar gauge stagnation. So once I press OK, this is using the global junction edit feature where I've now told Fathom what data is going to be required for that assigned pressure. I want to apply it to these 6 assigned pressure junctions, select all my data, apply, and then press OK. And now that will go and save that data in all of my assigned pressure junctions. Pipes, we're just going to simply say that the first pipe is going to be our working system. So we're going to be working with a steel ANSI 12-inch pipe. And we're just going to say this is just 1 meter long so that it's just atmospheric leading up to that pump. Not much special with that. And then for our other 3 pipes here, using global pipe edit, we're going to say that it is that same 12-inch ANSI steel pipe that we're going to be working with in our real world simulation situation. And this is saying that we're going to want to move this fluid 700 meters. So we'll put 700 meters there. So apply a selection, press OK. So now the only thing left within my model, everything's defined here except for the fluid that I'm working with. So we'll create a child scenario, and we're going to start up with our scale up scenario. So now we're going to start talking about our fluid and ultimately what we care about right now, our viscosity model. So starting in our fluid panel, let's look at user specified. This fluid is going to be 1,130 kilograms per cubic meter as the density. And as a starting viscosity, we're just going to place 0.001 kilograms per second meter for the dynamic viscosity. It's important to note that as soon as we change our viscosity model, this dynamic viscosity is no longer going to be relevant when we're talking about using a power law or it being in plastic, because those models are going to calculate the viscosity a different way. This is only a constant. So with those data points fine, we're going to go over to our viscosity model and change this to homogeneous scale up as our first example. That's where we have our data from. And we're going to enter this scaled data here. The homogeneous model, scale up model needs to know what was the test pipe you were working with. So you would specify a pipe material, in this case steel ANSI, the size of the pipe that we did our experiment in, because maybe the experiment used a different line size. In our case, our experiment used the 8-inch line or a 203 millimeter pipe. And we had data in that table. I'm just going to press copy in the data from a text file that I have available. So by pressing this edit table, import from file, I have my text data for this scale up data here. Press open. It's going to import my data and in the format that I choose. And so it is a comma separated data type file. So we're just going to say comma. There was no header, so we're going to ignore that. We'll press OK. And it will have pulled in my data for my velocity, my head gradient, and my flow regime all for me. If you're following along with that non-Newtonian phosphate slime example from our help site, do note that the pressure, that text file comes in a meter per meter value. So cool. So with that available, we can now go over here to our graph tab and we can see how is this pipe, our test data, going to compare to our real world pipeline. So we have test data for an 8-inch line. We want to use a 12-inch line in our real world. So we're going to say, let's cross plot these two curves against each other. I'm going to say what is the pipe type that we're going to be looking at. We're going to choose steel ANSI, 12-inch standard, and then press update graph. And that's going to show me here the original head gradient versus the velocity shown in blue for that 8-inch test data, and then Fathom saying what would that gradient look like if we were instead using a 12-inch pipe, so it's scaled up. So with all that, we can press OK, we can press OK again, and our entire model is defined. We can save it, we can run it, and we can go over and look at our output. What's of interest is if we go over to our pump summary, we can see that the pumps, how is it calculating what head rise at what flow rate is needed. So this is a way that you can figure out how to size your pumps, find a pump curve that works well for you, estimate what is the overall power that's going to be required by that pump to be moving your non-Newtonian fluid. Some other values that might be of interest to us when it comes to these non-Newtonians is if we think about our pipes, maybe we care to see that gradient. So let's do that head gradient. We'll add that. Let's do a pressure gradient. We'll do the stagnation total and show that in meters per 100 meters and bar per meter. So we can see what is our head loss going through that pipe with our scaled up fluid that we're working with. So that is the scale up example in a nutshell. We can also, now that we're within Fathom 13 using workspace layers, all this can be displayed on the workspace for you. So I'll show you how to do that here briefly. By pressing this green plus mark, that will give you a new layer. I called it labels. Pretty simple, just straightforward. What do you want to call it? Go into the layer settings. The first thing I need to do is specify what pipes and what junctions am I wanting to display data for. I only want to display data for our 700 meter pipes, 2, 4, and 6. And we'll display data for our pumps as well. Going over to pipe parameters, values that might be of interest to us includes the diameter, and as you can see, the moment that I add it to the right hand side, it will display for me on my workspace. Other things that might be important is my velocity. Let's look at the pressure gradient, stagnation total, head gradient, and then for the junctions themselves, we can care about the head rise produced by that pump, the volumetric flow rate provided by the pump, and then the power that was required for that pump. So all of that can be displayed right there on the output for you. So now we have a base template using the homogeneous scale up as a way to model this non-Newtonian fluid. Let's also look at what it would be like to model this as a power law fluid. So if I right click on here and say clone this scenario without children, we're going to go look at the power law model next. Going to analysis setup, I can change my viscosity model to the power law. If I had coefficients that I either calculated for myself using Excel data, maybe I went and curve fit that power law relationship and I have coefficients available for me. Otherwise, I can calculate it from a rheological data if I have the shear stress versus shear rate. So let's say that we have shear stress versus shear rate data. So we're going to calculate it from those values. In the example, we have tube flow rheometer data. So we'll open that up, import it, And the shear stress for that example is in a rate of hertz per second, and the shear stress is in pascals. So once I've entered in my data points here, I can generate a curve fit from it. So there's my data points on a log-log scale, telling me what would my K and N value be if the fluid we were working with was a power law fluid. So I press OK, and it will then enter those coefficients for me and show me that shear stress versus shear rate data accordingly. So we'll press OK, and now save and run our model again. So we could go back here and look at how much head is required for being predicted for this fluid. If it was a power law fluid, what the power was required to run those pumps. You also see here this warning. What Fathom is also able to do now that we have a different viscosity is we can see, well, one, what is the viscosity of the fluid we're working with at different flow rates, as well as the Reynolds number. So we'll press OK there, and we can now see what the viscosity at that flow rate was, along with a Reynolds number. So we can see that we're in the laminar region until the end, where we're now in the turbulent region. Third model that we're going to compare right now is the Bingham plastic. So again, we'll clone without children. Go back to our workspace, go to analysis setup. And we're going to change our viscosity model to a Bingham plastic. If I had coefficients, I can just enter them right here. Instead, we have rheological data for the example, so you can calculate it. Thankfully, it just saved for me from my power law. So we'll generate a curve fit based upon, yep, that's in pascals, good. So now it has my plastic viscosity prediction and my yield stress prediction for what point does it start to, the fluid will start to move. So we'll press OK again a few times, save and run our model. And now that we have data for all three of these models, one, what we've seen now is how can we enter the data, but let's think about how do these stack up with each other. The interesting thing about models is fluids can either line up really well with them, or they can kind of be split between different models, and you have to use your engineering judgment of what fluid viscosity model is most appropriate for your working fluid. And then also, how do you predict the head rise for your pumps, sizing pumps, systems, etc. So if we go back here to our scale up model, let's go to analysis setup. We'll go back to our enter scale data. We'll go to the graph. Let's see how Fathom would predict that the power law or the Bingham plastic model would compare to the fluid we're working with. So if I press this cross plot correlation for test pipe diameter, here's our power law. So as we can see, it's lining up with those data points really well right up until it starts transitioning into the turbulent region. So we can see that's where the power law is transitioning. So we can say that this fluid probably matches that power law regime pretty well. And so whatever the power law is predicting can be kind of comparable to the scale-up model. If instead this was a Bingham plastic, we can click on the Bingham plastic radio button and we can see how that would compare. And for the most part, in the lower, slower regime, we can see that the data points are lining up pretty well, but then the Bingham plastic starts to diverge away from the scale-up model. This may be an indication that the Bingham plastic model would predict a greater pressure gradient than would actually be seen by this particular fluid. So let's go look at that. So cancel, don't want to clear my data. And let's compare these three side by side using a multi-scenario comparison. So we'll say output control, go here to multi-scenario, select scenarios. We'll pick up the scale up, the power law, and the Bingham plastic models. And now we can see the pumps side by side with each other. So in our scale up and our power law fluids, we can see that the head prediction for this model is practically the same. Power is slightly different. The Bingham plastic is very akin to it in the slower regions. Remember, if we look at how our let's add Reynolds number and viscosity to our pipe real quick. For our Bingham plastic, we've been in in the slower pump, we're in that transition kind of region, and then finally at the end, we're in the turbulent region. Same with the power law, as we can see. And so when it starts to get turbulent, that Bingham plastic may start to separate further away from our homogeneous scale-up model. And we can see that here if we look at our third pump, pump 8, which is pumping out 1440 cubic meters per hour. The scale-up and the power law are pretty neck and neck with each other in what they're predicting, but the Bingham plastic is predicting a greater amount of head rise. Another indication that when we were looking at the analysis setup, that Bingham plastic is moving away from our data, and so it may not be a good representation of what fluid that we are working with. So there you go, that's a way to be able to see three different non-Newtonian fluid models within our software, how you can quickly compare them side by side and try and figure out which would be the most appropriate for you. And as always, you should also be talking to your fluid manufacturer, especially if you're working with some sort of polymer or a slurry example. It's always best, gold standard is go get rheological data for that fluid that you're working with, so that you know exactly what fluid you're working with and which model to select within Fathom in order to get the best results. So I want to thank you for attending this webinar. If you have any questions, please feel free to reach out to us. You can reach out to us at webinars@aft.com. You can also give us a call at 719-686-1000. That is our main number here at AFT. If you have any questions, want to contact us for sales for the software or ask support questions. So again, thank you for participating, and I hope you have a great day.